So lambda here is wavelength. And again, that little wave on top reminds me it's a wavelength. This V is actually nu, and C is your speed of light. That's your constant. So you'll use this to calculate either frequency or wavelength, depending on which one you're given. Okay, again, that common misconception that radio waves are slower than gamma waves. Let's go back up here. This is not true. They all move at the same speed, which is the speed of light because they're all light. They just have different wavelengths and frequencies. Okay? So, one of the things that led to some of their new knowledge was the photoelectric effect. And this started them thinking again that light might actually behave as a particle because at this point in time, they decided that light was a wave. And what this is energy of light hitting metal. And some energy popped off an electron and some did not. Now, they hypothesized incorrectly, which is why they needed to come up with a new model. Okay, so the first thing they did was decide that these were energy packets called quanta. So that meant that energy came in these distinct packets, not exactly whole numbers, but they came in steps. So instead of going up a ramp where I'd go through every single centimeter of height, it's like going up a ladder where I go up in chunks. Okay. And they came up with this other formula that the energy equals Planck's constant times the frequency. So if I knew the frequency of a wave, it related directly to energy multiplied by this constant. And Albert Einstein decided that these particles that carried this energy was a photon, and it's basically a particle of light, and that's how Albert Einstein described it. And you could find the energy of that photon using this equation again. Okay, so he decided that matter could only absorb a whole number of photons, and those are those chunks, those quanta of energy. So, why did some streams of light knock out electrons and some didn't? They thought that they could raise the intensity and that would raise the energy and knock it off. That means they could raise the amplitude of that waves. That was one of their incorrect hypotheses. I had a hard time wrapping my brain around it. You might too, until I came across this analogy to elephants. Okay, so basically, if I fire a cannon at the elephant, it's going to knock him over. Okay, it doesn't matter if I fire one or 100, it's going to knock him over. It has enough energy to knock him over. However, if I fire a ping pong ball, it's not going to knock over an elephant. And they thought that if they raised that intensity, which would be like shooting tons more ping pong balls, and it's low energy still because it's just a ping pong ball, that it would knock over the elephant, but it doesn't. And so that's kind of the analogy. And you can explore that photoelectric effect at this simulation here and the video that really explained this well. And I had another teacher who told me this when I was younger also. Here's a link to that video to explain that photoelectric effect in more detail. So now they're really starting to formulate quantitative analysis where they can calculate things. And they do have some qualitative analysis coming up where they visually see things. The difference is quantitative. Quantity deals with numbers, and qualitative is your five senses. It does not deal with numbers. So they passed light through hydrogen, and they thought they would see all the colors of the rainbow. They thought they'd see the full spectrum. Instead, they saw these distinctive lights. And this was another way that scientists started developing more and more about this theory. Okay, and they're wondering, why do I just have these certain lights and not all the lights through the spectrum? Well, if we're talking about as a particle of light, is these particles, these photons, give off energy. If it's in certain packets, you'd get certain lines instead of the whole rainbow as it passes through all the energy levels. So this was just another piece in the puzzle to say that these energies that are given off are in these big chunks, okay? And the Bohr model really explained this very well, okay? So I'm going to skip down and go over that Bohr model with you. So what happens is we have this Bohr model where a nucleus is in the middle, and we have these energy levels, which are these rings, and Bohr thought that the electrons actually orbited the atom. That's not true, but this model works so well to explain this that we still use it today. So basically, if I have this electron, and this electron is at ground state, which means it's the lowest energy it would be in an atom. It can gain energy and jump up energy levels, okay? And it's absorbing the energy to jump higher. Now, as it relaxes back down, so here is my photon, it's going back down to ground state, back home. It gives off energy to get down, and this energy, these packets of energy, are what you see in the spectrum for hydrogen, and we call the emission spectrum basically a fingerprint for an element. Every element has its own emission spectrum. So as hydrogen electron came down, depending on how it came down, it would emit certain packets of light. And we'll go through that in more detail. When it went up, very interestingly, it would absorb light. And here's the absorption spectrum. And you can see black lines where it absorbed that light, and it's gone because it took that energy away. Okay, so here is a little cutout of our Bohr model. And we have the Balmer series, which I'm going to focus on. You don't need to know the names of the series, but Balmer series is when these electrons went from different energy levels back down to energy level 2. Okay, and this correlates exactly with our visible light spectrum. So when it went from, say, 4 down to 2 or 3 down to 2, it gave off different colors of light. And these lights on our hydrogen emission spectrum are the electron falling from different levels, okay? So we need to understand how to use this Bohr model and how to draw a Bohr model with other elements and other electrons. So here is using the Bohr model, okay? And the Bohr model not only predicts energy of light absorbed or emitted, but we also use it to predict reactivity in elements. It doesn't go over all the properties of the elements. It doesn't explain all of them, but it can predict reactivity. And why is that? Well, here's the picture of our Bohr model. And here is our atom. When two atoms come together, the only thing that touches are these outer rings. And that's because electrons are negative. So when another negative electron from another atom comes near that, they start to repel. So they really can't get much closer than the rings, the two outer rings, having a chance to interact with each other. They don't really overlap and get inside. So these outer ring electrons are called valence electrons, and they are the electrons that participate in chemical reactions. The inner ones do not. They are shielded by these outer electrons. So in order to draw this Bohr model, we draw the nucleus. Here's our nucleus. And we have 11 protons and 12 neutrons. You can figure that out from your periodic table and your atomic number and your atomic mass. Now, for a neutral atom, if I have 11 protons, I have 11 electrons. How are these energy levels filled? Well, here are our rules for filling the energy levels. And basically, our energy levels are labeled with the letter N. So N1 is our first energy level, N2 is our second energy level, N3 is our fourth, and so on. Those are called our primary quantum numbers, okay? And your primary quantum number is your energy levels. And you'll notice on the left side of your periodic table, you have numbers going down. Those also correspond with our periods. Our periods are energy levels. So this is sodium, and sodium has 11 electrons. My first level can hold 2 electrons, so there's my 2 electrons right here. The second level can hold 8, so I put in 1, 2, 3, 4, 5, 6, 7, 8 more electrons. So right now I have a total of 10 electrons, but I have 11. But this energy level's filled with the 8. N2 can only hold 8, so my 11th has to go in my N3, or my third energy level. And that means my outer shell, my outer energy level, only has 1 electron. So that's your valence electron. So here is an example here. And you can see that my valence electrons they're only 1 there. Okay. So I'm going to go over this tomorrow, but I do want you to know before we go in there that we're going to be drawing them like this, but our energy levels are not evenly spaced. And here is a Bohr model of a hydrogen where you can see the energy level between N1 and N2 is the biggest gap. That is the biggest gap between energy levels. And then as I go up to N2 and N3 and N4, my energy levels get closer and closer together. So a lot of times when we look at these energy levels, we take a cutout of this Bohr model right here, and we just look at the line. So our nucleus would be down here at the bottom, and then N1 to N2 is our bigger gap. It's a much shorter jump to get to N3, N4 even shorter, and the energy levels keep getting closer and closer together. So now we're going to work on a worksheet and practice drawing these Bohr models. And we're also going to work on introducing the Lewis dot model, which is how we only show the valence electrons in an atom. And that's because when we talk about reactivity, we only care about that outer shell. So Lewis made another model that just shows the valence electrons are the only electrons that participate in the chemical reaction.